So now we return to our slides, and the last time we were using this, we made this statement that the plasma parameter, which is essentially NE times lambda d cubed, is a measure of the dominance of collective interactions over not just collisions, I mean binary collisions. Okay, so I hope it's clear that what I really mean here is that binary collisions would be a positive and negative charge directly colliding with each other. So if the negative charge was trying to go in a straight line trajectory, it would have a large angle deflection. However, if there are lots of positive charges and lots of negative charges, so on and so forth, lots of them, and if there were lots of them and there was a negative charge trying to pass through here, what would happen is it would suffer small deflections, like this. Okay, so this would be a large plasma parameter kind of scenario, and this would be a small plasma parameter kind of scenario. So here the collective interactions, okay, the cumulative effect of several small angle collisions. This is what matters in this scenario. Whereas here, a single large angle collision dominates. Okay, and so this would be a quote unquote sort of a good plasma. This, by contrast, would be an example of a bad plasma. No such thing, but you get the idea. Right, so I wanted to, the more particles that are in a device sphere, the better the central charge imbalance is screened. So there are fewer direct collisions. I really should not say Coulomb collisions. Direct. By direct, I really mean two-body collisions. Everything is Coulomb. Okay, so all right. Moving ahead. Why is it doing this? Right. So moving ahead, this is what we just said. The cumulative many-body effects far outweigh the binary, in other words, the two-body large angle collisions. Okay, so now we've done this too. Consider the smallest impact parameter arising out of balance between thermal, which would be this, and electrostatic energies for two-body collisions. So this would be the thermal energy. A half energy, this guy, and this would be the electrostatic energy. This guy. Okay, so equating the two gives you some idea of the smallest. This is essentially what we call the B classical, the smallest impact parameter classically determined. Okay, so if you right, and the probability that a particle will undergo such two-body collisions is just NE times B cubed. Okay, where B cubed is the volume like that. Okay, that would be a radius B, and so it's strictly speaking 4/3 pi B cubed. But for simplicity, so consider a sphere with radius B, where B is the impact parameter, the smallest impact parameter to be precise, and you multiply that with the particle density. That gives you a dimensionless number. That's a probability that a particle will undergo these kinds of small two-body collisions. Okay, all right. Now, substituting for B. And substituting for B from here, and using the definition of the plasma parameter, this is simply Ne. Okay, and substituting, of course, for the expression for lambda d, you get this probability that all of this, by the way, is from Starok. Okay, the probability that a particle will undergo two-body collisions goes as the plasma parameter raised to -2. So, if the plasma parameter is much larger than 1, the P2 is very small. The probability of two-body collisions is very small. That's what this statement is saying. And if you wanted to, in other words, two-body or large angle collisions are rare. In fact, three-body large angle collisions are rarer, even rarer. I haven't gone into those details. Please refer Starok. Now, therefore, the converse of this statement is that if two-body direct collisions are rare, what's more common? Well, many body effects or collective effects. Okay, so this is what we've been building up towards, and so let's consider what are these collective effects. Let's think about this in some detail. Now, one way of thinking about this is as follows: simply taking a relevant length scale and a relevant time scale, and this is the approach Boyd and Sanderson take. And so let's consider that first. Clearly, the relevant length scale for collective effects, in other words, the length scale over which charge neutrality can be thought to be established, is the Debye length, right? It's only outside of the Debye sphere, well outside, or say outside the Debye sphere, the plasma can be considered to be quasi-neutral. Right? So it's in that spirit that we say the relevant length scale over which charge neutrality can be established is the Debye length, right? And the relevant thermal speed, and the relevant speed is the thermal speed. Okay, why? Well, you're not talking about a single speed electron, really. I mean, you're talking about an electron that belongs to a distribution. What kind of distribution? Well, a Maxwell-Boltzmann distribution. And what's the typical speed in a Maxwell-Boltzmann distribution? It's a thermal speed, which goes as square root of kTe over me. Now, what you do is you divide one by the other. So what this is saying is that the question we're really asking is, how is charge neutrality established? Okay, the electrostatic fields that establish charge neutrality will cause oscillations about an equilibrium position at a characteristic frequency called the plasma frequency, which can be obtained. So this has the dimensions of frequency, speed divided by length. It goes as 1/second, okay, 1/time, and so this is what's called the plasma frequency. And the plasma frequency, when you plug in for a VTE and lambda d, that's what it looks like. It goes as a square root of the electron density. So this is the main thing. Omega PE is proportional to Ne raised to 1/2. This is the main takeaway from this. As such, you simply divided velocity by length scale. That's all you did. But the physical implication is that, this quasi-neutrality is established over a time scale. You see, what happens is, and this will be a little more evident from our next treatment. In other words, you disturb the system from its equilibrium. In other words, you disturb it away from quasi-neutrality, and what will happen is there will be oscillations which will happen over a certain time scale, okay, and before the system settles, you know. So this is a much more evocative, this is a much more you know, transparent, physically transparent treatment from Starrock's book, to the same end, to deriving this expression, to establishing this formula for the plasma frequency. Okay, so what you assume is that the electrons are all static. Okay, so they're totally static. In other words, since they have no random motion, so static ions means no random motion. So same thing as saying chord. Okay, and what you do is you have you know, a sheet of electrons, one dimension, like that. Okay, plain parallel sheet of electrons, and so the equilibrium, and so suppose this would be the x dimension. Okay, and the sheet of electrons originally at some x is displaced to some x plus psi. Okay, so it was originally here and it's displaced to some x plus psi. As a result of this, there's an excess charge of n, and n is the number density of electrons, of course. So n e psi per unit area to the left of the sheet. Okay, excess here, okay, and deficit here, because you displaced, you brought some negative charges to the right, right? So the deficit of the same amount. So therefore, you have a net electric field. You have a net charge, and therefore a net charge gives rise to an electric field, right? Electrostatic electric field. Yeah, and so this is the net charge, and so from Gauss's law, E is equal to this, and this is written in CGS, which is why you have this 4 pi appearing here and no epsilon. Okay, so that's fine. E equals that, right? And the equation of motion ma is equal to F. ma is equal to F, right? This is F and this is ma. So what are we really implying? What we are implying is that you take this one-dimensional sheet and you displace it to the right, okay, and you will immediately recognize F equals ma, this kind of an equation, to be an equation of a simple harmonic oscillator. So you displace it to the right, it will bounce back, it will overshoot, and then it will go back, and in the absence of damping, it will keep going on forever. Okay, with a characteristic frequency given by square root of k over m, right? Yeah, or instead of this d square, you just rearrange the terms, and you get a frequency here, where this frequency, the way you rearrange the terms, the frequency is simply given by this, the same expression that we saw in the previous slide. Okay, so this is the plasma frequency, and so this is essentially SHM, simple harmonic oscillations. So this is a slightly more transparent, a little more physically appealing treatment, I would say, of this plasma frequency. And this is what collective effects. These are the so these plasma oscillations are all about collective effects. Okay, it's a collective behavior of this system. Okay, and so the oscillation frequency is this, and as before, PE proportional to any raised to 1/2. That's all you need to know. What is the plasma frequency of a given medium? Well, you tell me the density of the medium, and I'll tell you the plasma frequency. Okay. So this is the sort of the main illustration of collective effects in a plasma, the plasma frequency. Okay, and you can one mechanical analogy that people often resort to is a bed of springs. Like your mattress. Like that. Okay, and you have a mattress sitting on it. Okay, and you jump on it. Okay, jump on the mattress. Okay, it oscillates. At a characteristic frequency. Characteristic collective. All the springs oscillate at the same time. So this is one analogy that's often used while describing plasma oscillations. Okay. Right. So yes. So there are some caveats. Coming back to the thing of this picture of electron sheets, quasi-neutrality is still there because you've got the assumption is there's a immobile static ion background, a proton background, if you will, and the amplitudes need to be small. Very important. If the amplitudes are large, then this entire treatment breaks down. The motion needs to be simple harmonic. Again, small amplitudes are also sort of go hand in hand with simple harmonic motion, and the electron sheets cannot cross. This cannot cross the other, and there are no particle collisions. Okay, which causes dissipation of energy. Collisions go hand in hand with energy dissipation or damping. Okay, and the whole treatment does not work if the motion is not planar. Okay, so this entire very appealing treatment works only for 1D motions. You cannot, for instance, consider a cylinder like this and immersed in one more cylinder like this, and you displace the cylinder a little bit and doesn't work. Okay, it's important whenever you come across a simple, physically intuitive, nice, cool kind of way of deriving something. It's nice, but you should also be very aware of the limitations. This model has its limitations. Okay, nonetheless, the plasma frequency concept is an amazingly useful one in practice, and this is in practice is what we will focus on from now on. In other words, where or in what circumstances is the plasma frequency manifested? Where does it, manifest itself? We will talk about this very soon.